Hi, and welcome back to Codex. Our speaker today is Shira Faigenbaum-Golovin, who is a Philip Griffiths Assistant Research Professor at Duke University. Dr. Faigenbaum-Golovin is an expert in numerical analysis, mathematical modeling, and high-dimensional data analysis. Today, she'll tell us about the approximation power of neural networks. Take it away, Shira.
Thank you, Emily. Thank you, Emily and Dustin, for organizing this seminar and giving me the opportunity to speak here. And thank you also for bringing this amazing community together, although we are very far away from each other, but it's nice to see how everyone are joining and listening to interesting talks. So without further ado, let me start my lecture for today. I'll try to address several questions that mainly are somehow related to the approximation power of neural networks. I will start with talking about manifolds and high-dimensional data. This is a work that I was doing while doing my PhD with David Levin in Tel Aviv University. And later, I will shed light on newer topics that we are now dealing with Ingrid Debussy and the amazing group of people that are involved in this. And let us start talking about all of that. So, I'm coming from approximation theory, and I would like to think about the neural networks in the terms that I'm used to. So if we have a function that gets some input x and result with some y, and let us emphasize that we usually don't have the function that is doing this operation, but all we can sample and acquire the data are x's and y's, whether it's images and the classification of those images, whether it's some other data that exists out there, but that's the data that is available. Once we try to build those neural networks, we try to construct an architecture that will reconstruct or approximate the original function in the best way that's possible, meaning that we are trying to minimize the predicted y hat here with the value of the original ones. We are trying to find the optimal parameters that will do that. Now that we have the settings of these neural networks all clear, let's move and talk more about what's really happening. It's already known from the 80s that the neural networks produce universal function approximates, meaning if we have a target function f and some accuracy level epsilon, we can construct with a given number of parameters, a neural network that will approximate in the required order epsilon. But it's still not clear why those amazing neural networks are working. We see numerical experiments all over the world. They are just swiping our mind, but we still have some blanks in the theoretical parts. I list here just a few groups that work in this endeavor, and they try to tackle the problem from the approximation theory perspective. If you know more groups, I would be happy to list them here also. So please drop me an email about it. But still, the problem of neural network approximation is far from being clear. What are the components that can influence on the order of approximation of the result? So first of all is the input data. What is the geometry of the input data? Can we say something about it? Can we say something about the field distance, how densely the samples are acquired from our domain, and how is it related to the approximation order that we can expect? Next is the function that we just saw, that one that brings from x's to y's. If the function is simple, maybe linear or something like that, it's probably easier to approximate it with neural networks. But what happens in the more complicated case? And naturally, the architecture of neural networks is also plays a big role here, because we all know that it's very popular to construct deep neural networks with large amounts of parameters, and let's see what happens. But how do we build those neural networks wisely? And last and not least is another aspect. We just mentioned that we are looking for the optimal weights in the nodes of those networks. But also, what influences the approximation order eventually is the optimization procedure. There are some works that have been done that show that the gradient descent is very unstable in terms of the initial parameters that it receives. So it also affects all the process. So we see here that at least we have 4 components, and I'm sure that there are more, that influence the approximation result. I will focus on 2 of the first ones today, on studying the geometry of the data, and also of trying to understand what functions can be approximated by neural networks. And today I will add additional class of functions, the refinable functions, to that list. So let's start from high-dimensional data and its geometry. We all know that life is not a Swiss roll. We like to play with toy models and nice examples, but the truth is that in data, in digital humanities and data science, the data that we have is in different, coming in different geometry. Not only this, we usually do not know how it looks like and how, whether it was sampled from a manifold, what is the amount of noise that exists out there, what is the intrinsic dimension of the data, and much, much more. We can assume any assumptions what we want, but the truth is that we are totally in a black room and trying to study the data geometry. Usually what we perform in that case is dimensional reduction, but we have to do it very carefully because we make assumptions that later can influence the result and the analysis. Instead of doing dimensional reduction, we can still try to analyze the data in high-dimensional case. And that's what I will propose doing today. So one of the main problems of high-dimensional data that lies on manifolds is the problem of noisy settings. And it's also a problem if we get such data in neural networks. So the setting for the problem are the following. So we have some manifold M, and it's reasonable to assume that the data that we receive in our networks coming from a manifold, because usually the data is acquired from some common domain, for example, pictures of cats and dogs, and we can assume that the data was non-uniformly sampled from that manifold. Once we have this manifold with intrinsic dimension d that is much smaller than the real dimension, and some data points p tilde that were sampled with noise, without noise from that manifold, usually what happens that we are not getting those noise-free samples, and what we are observing in our data acquisition are p points, which is the set of all the PGAs that actually contain noise and outliers. So what is our first goal in this case? We would like to reconstruct the original manifold and denoise the data, meaning we would like to approximate how the manifold really looked like in various scenarios. There was a lot of work done in this direction, starting from the works from Chen et al. And continued with many brilliant people, but most of them didn't address the problem of noisy scenario, of noisy non-bounded noise scenarios. And those that did address that, like Sober and Levin, had some assumptions on what is the intrinsic dimension of the manifold. So when we started working on that, basically that was the situation. And we proposed a method that performs denoising and reconstructing manifolds. So what we are looking for in our reconstruction are actually the set of points Q's that will reconstruct the manifold. And how do we do that? We propose to look for those Q's in terms of some kind of non-convex optimization function. We construct the optimization function in the following way. We have 2 terms. The first term, which is responsible for keeping the proximity of the new set Qi to the original points Pj. We are not doing it globally, but we have some Gaussian weights here that actually narrow down the problem to only the close neighborhoods in the support of this Gaussian term. The next term, which is balanced with the lambda I primes, is term that is responsible to spread all the points over the manifold. We have some eta function here that is punishing the points that are getting too close one to another. In our case, we took eta is 1 over r to the third. Now that we have this non-convex optimization, we can perform gradient descent and look for the optimal Q that will perform and reconstruct the manifold. I hope I convinced you, but if not, we have an example here. This is a 6-dimensional cylinder, which is a toy example again, but that's how I can evaluate that the proposed method really works. And it was embedded in R16, and a noise was added to it as well. And what we see here is only the 3 first coordinates of this 6-dimensional cylinder with noise. The original points are the green ones, and the ones that are responsible for the reconstructions are the red ones. We subsample them from the original point, and we perform the gradient descent iteration. As we see, those points are evolving each time, smearing the local neighborhood, and somehow reminding us the KL1 median locally. And while the second term that is responsible for the repulsion are pushing them away from one another. That's how we reconstruct the manifold in a quasi-uniform way. To support this, we have some theoretical results about that. It was really hard to prove something about this non-convex function, but eventually we were able to prove that the gradient descent indeed converge almost surely to a local minimizer with approximation order of h squared, when h is related to the field distance of the points p, the representative distance of the set, the initial set, that we indeed, as we expect, receive a quasi-uniform distributed points all over the set, and we can also bound the amount of iteration that is needed. So, okay, we ran some numerical examples. We were quite satisfied about that, and we decided to extend it. I will not talk about and get into details to the works that follow that, but I will just briefly mention that we also extended the method to approximate function of manifold, as well as repair missing and complete missing information in case we have holes. All of this in high-dimensional space. Now we are working on a problem that is somehow related to the neural networks. When we have a limited data that was sampled from the manifold, this is the picture that we see in the middle, and we want to this is what was available, because sometimes it's very hard to sample and also label the data that you sample. In historical settings, it's maybe I will say it's practically impossible. And what we would like to do is enrich the data set that we have. So using our method, we can, from the one side, we can compress the data, and then we can decompress it and recover maybe information that we want to upsample the manifold. I'll not talk about this more, and I'll end this part here. If you have some questions about the manifold and high-dimensional data, maybe it's a good point to stop here and ask it, because I will be moving to the other aspects of refinable functions and neural network approximation. Are there any questions about the first part?
Could you go back to the slide with your loss function?
Yeah. So here we have those Q's eyes that we are looking for them to be close to the PJs, the original points. This is the first term that we have here. And we are looking on those locally, meaning for each QI, we are looking for the points PJ that are in the local support that is defined by this Gaussian and the H1 that we have here.
So when you use this, do you have a method for picking the bandwidths that you prefer? The H's?
The H's, yes. The H's, it's I agree that it's always challenging to pick the right H, because from the one side we don't want the support size to be too narrow, and we don't want it to be too big either, because then we can be on the other branch of the manifold. And we propose some method how to find those H optimally. It differs from whether we're talking about the P set or the Q set. That's why we have two different H's here. And it takes into consideration basically the idea how many points each QI will satisfy from the P set. Once we have this guess, we can demand that those points will be always available in our support of H1 size.
So you're like implicitly trying to make like the graph of connected points like somewhat regular?
Yeah.
Okay, thanks. That's really helpful.
Because usually what happens that the amount of PJs and PIs is not the same. And we should always look how many points should each QI or each Q and PJ have in its local support, and that's how we choose the H's. That's a good question.
Thanks.
More questions? Okay, so let's move to the second part. So the second part is related to the function that can be approximated by neural networks. And can we add something to this part? So it is known that the smooth functions, such as polynomials and analytical functions, can be approximated. It is also known that very weird functions that is nowhere differentiable, like Weierstrass functions, also can be approximated. And there is a list of others that can be approximated, although it's not very big. So today we will add to this list the functions that are acting based on some recurrent equation, meaning the refinable functions. We will narrow down our analysis only to networks that are the ReLU networks, meaning that the activation on each node is the ReLU function that is the maximum between 0 and x. And we narrow down to this scenario because those are usually functions that are heavily used in the numerical settings. And also it's, I would say, kind of more easier to understand what's going on with them. And it is known that the output of the ReLU networks is the continuous piecewise linear functions, which we'll be meeting along our way today. So the question is, what is the type of function that the ReLU networks can approximate? And let us define the first definition. Let us look on all the functions, on the vector valued functions that are generated by the fully connected network with a width of W, depth of L, an input dimension of D, and output dimension of N. And in addition that they have the ReLU activation function. Okay, and if it's still too wide, let's narrow it a bit more. We are looking on all the functions that are approximated by those networks with only one input and only one output. And as we will see, it will be enough to approximate the refinable functions. So this is the first takeaway message from today's lecture, that the refinable functions that we'll be talking about them, and don't worry if you don't remember the definition, or if you do, then I need to apologize for the next slides, that the refinable functions can be approximated up to exponential accuracy with ReLU networks with fixed width and increasing depth. And that is a very interesting result that we recently published with a great group of people. And I'll be describing that today. But before that, diving in, let us just remind ourselves what are the refinable functions. Those are functions that follow the following equation. If we have the function values at certain points, like we have here the points that are in 2x minus n, using some refinable mask Cn, which is given to us, we can reconstruct the value in a different point, f of x. And basically the difference between different functions that obey this equation is the mask that we require and for them to follow. This was first suggested back in the 90s by Alpert and Rocklin, and later it was in parallel, it was studied by Debussy and Lagarius, and there are very interesting and nice properties to those functions. And I hope I will be able, in the half an hour or more that we are left, to summarize some of the results that they had. So what are those functions? Those functions are actually, we like to play with them a lot in our daily life. Those are the B-splines that follow the refinable equations, the subdivision schemes, which are widely used in CGD and computer graphics, and multi-resolutional analysis framework, the wavelets, the fractal-like objects, and also the attractors of hyperbolic iterative functions, that some of them were suggested by Bernsley and appear here. So, and there are, the list is quite long. I just listed just a few of them. So I hope I convinced you that if we add this class to the ones that can be reconstructed by the neural networks, we will be quite happy with the result, because it covers such a wide range of functions. Let us look on the concrete example of the quadratic B-splines, and I will try to illustrate what are the functions on this example, and how do we deal with them. So we all know the quadratic B-spline equation, which basically has the values in 4 nodes, and with the refinable mask of 1/4, 3/4, 3/4, and 1/4, we can reconstruct the value in addition in the next point x. Let us rewrite this equation in using the CI notations that will resemble the refinable mask that we all know. And before going to a concrete example, I want to rewrite this equation in a matrix form. For doing that, I will need some tools that we will introduce now. First of all, let us look on the binary expansion of an x that belongs to the range of 0 and 1. The binary expansion of x can be written as the sum of the bits bi, which can be either 0 or 1, multiplied by 2 to the power of -i. And if we are looking on the bits, we can extract the q. We can define the qx, which will be the step function on half and 1. This will basically define us the bit extraction operation, the way that we define and extract the bi's. Now let us define the residual that is left from this bit extraction. The tau x is 2x minus qx, which is in our, if we substitute that qx is either 0 or 1, is the following thing. So we are either in the case of 2x or 2x minus 1. And we know that this function is naturally not continuous in a half. And this will play a big role in later operations. So once we introduce that, let us go back to our quadratic B-splines, and let us rewrite them in a matrix form. So we define the vector value function Vx as the values of the B-spline in those dots. And we can now rewrite it using the bit extraction operator as in the following recurrent way. So the V, the vector value function, is actually a matrix multiplied the operation V in the point after doing the residual on the x of tau x, where the TB of I are basically represent whether the bit is 0 or 1, and the matrices are defined in the following way. And those are the coefficients, if you remember, that we saw in our B-spline refinable equation. Okay, so let us do this operation on a concrete example. So on B-splines, we have the values in -1, 0, 1, and 2. And now we iterate and calculate the refinable equation for points that are in the middle of those the existing points. If we perform it long enough, we iterate for many iterations. Eventually, the limit function which exists will be continuous, and also its derivative will be continuous. And it's not by chance that this happens in this simple example, but it was also proven in the list of series of papers by Debussy and Lagarius that it is indeed what is happening in the general case. That those refinable functions are the refinable process under certain constraints on the refinable mask converge to a continuous and the derivatives of this process are also continuous. Okay, so having said that, let's define the refinable functions now in the matrix for the general case. So we have the initial points that we already know, and we define them as the V0x in the entry of n. This is the entry in our vectored value function. Again, we define in the general case the T0 and T1 matrices that are the matrices that contain the refinable coefficients, the CIs that we saw before, but with certain shifts based on some logic. And the refinable equation can be now written in the following form: that the Vj is the T, the matrix that we just defined here, in the Bi based on the bits of the X, multiplied by V in the previous of the tau of J minus X, J minus 1 of X, meaning we are looking on the J minus 1 residual of X after extracting the bits. And we can now define, once we define this recurrent operation, we can actually extract the matrices that are hiding here in the V. And we will see that this will help us in the analysis. So how do those T0 and T1 matrices look like? So basically they contain those coefficients, like in the B-spline case, they contain the coefficients in some intrinsic logic. They are of size n. And we can see by performing some analysis on those matrices, we can evaluate the properties of those refinable functions. That was what was done actually in the work by Debussy and Lagarius. Okay, so I hope that by now we are all aware what are the refinable functions. There are those that are obeying the rule of a refinable equation. We can write this equation not only as an equation as we saw in the beginning, but we also can write it in a matrix form, which will help us to prove the neural network approximation. And let us continue with defining additional stuff. So we can consider the linear operator V that will take some function G, and we'll see what are the G's later, based on the refinable equation that we saw before. If we write it in the matrix form, we can actually say that V composed n times to itself will look like that. If you just remember where is it coming from, so it's all coming from the refinable equation, that all the T's are basically hiding here, the T's of the next step in the refinable operation. Okay, so now we have the V composed with itself n times valued in G, and we see that there, this is actually, this represents our refinable equation. And now I think we are ready to state the first theorem about it. So if we have a refinable function with the refinable mask of Cj's, and let G be any continuous piecewise linear function that vanishes outside of 0n, meaning it has a finite support, and we can actually, we know what the support is. and let V be the linear operator that we just defined, the refinable operator. Then the function V composed with itself n times on G is actually in the set of functions that can be approximated by the ReLU neural networks with input 1 and output 1, and with width and depth that depend on the number of n, which is the support size of this function, and the number of breakpoints of G. I will not get into details how we proved this, but this was among the first times that such a broad class of functions that was added to the ones that can be approximated by neural networks. So are we happy with the result? Yes. Is there something else that we want to do? So there were some issues that we found out during the proof of this theorem. Since I didn't give you the proof, you will have to believe to the issues that I raise here. There is nothing wrong with the proof, but it kind of made us do some tricks in order to fit the refinable functions to indeed be approximated by those neural networks. The first thing is related to the refinable function equation itself. That is, basically, it's not continuous with respect to consecutive dyadic rationals, meaning that if we have a support size and we approximate the function in a certain point, like we see here, if we move a bit and we are already in a different dyadic range, this will influence on the result of the approximation. The approximation will still be smooth under certain constraints, but the way that we are doing is not continuous. There are certain jumps that happen there. The second thing is the residual function tau that we saw before. I already mentioned that it was not continuous in one half, and if we are doing the residual multiple times, we are calculating on hx the residual, then we have the following scenarios: that we have jumps of discontinuity in all the dyadic integers. And that was a big problem when we proved the theorem. And in order to overcome that, we defined a continuous function tau, which we name it tau bar, that depends on alpha and beta. That it is the one that we use to extract the residual of the bits of x. And as you see, although it is continuous, but I think that you can agree that it's a bit weird if we think about the extraction of the residuals. It can be assumed that usually that's not the way that you would think about the extraction of the residuals of the binary extensions. It further is enhanced if we are thinking about the repetitive recurrent process of that happens during the refinable equation. For example, if we do it 4 times, this is how the tau to the power 4 looks like. And that's, although it's continuous, but it's not natural that such functions will really occur in reality. And this brought us to the third part of this lecture, that I would like to introduce a new family of multiscale functions, a new family of refinable functions that are easier to be learned by such neural networks. So the first thing that we can do, we can define a different tau. The previous one was not continuous and a half. Let's define one that is continuous and that will follow the following rules. Okay, we are quite happy with this definition. Let us look now on what was happening with the original refinable equation. And why did we have those jumps that are actually always looking on the support of the function at a certain point? So we had those CNs and we had those points that we're looking each time on them. And now we would like to define a new definition of those refinable functions that will be continuous with respect to consecutive points. And that was our main rule. We tried several definitions, and although they were good on paper, but our analysis on the continuity and on the analysis on the continuity of their derivatives failed. Eventually, we were able to come up with this new definition of the refinable functions, which will be continuous in the sense that we are looking for. So what happens here? We have, again, we split our discussion here into two. Basically, we split our discussion, what is happening on the evens and what is happening on the odds points. So in the even, we are still acting as we acted before. We are still having the same nodes that we are using for our refinable equation that are basically are multiplied with, again, with the refinable mask. But also what happened for the odds dots that we are using in the support is that we will use, instead of using the odd dots, we will use the ones that are in the mirror from our current point. So if we had some point that was had to use in its support for the calculation of the next fx, a point that is located in the odd location, instead of using it, we will use just the mirror even that point that is available. I hope this is clear. And in order to emphasize the mirroring operation, we will use a different refinable coefficient here, the dn's. Okay, so now we have those new refinable functions that we defined. We still need to prove all the things that exist for the classical ones. And before doing that, we need to write, we start writing them in the matrix form. So here what we have is that we address the even points and the odd points separately. We also address this in the vectored value function that we define. That is defined differently for the entries that are in the even place and in the odd place, based on the values of the functions that are available. We again define the refinable equations as before, but now we have different matrices, not the T1 and T0 that existed before, but we have something else, and I will talk about them in a minute. And we can also now define the refinable successive approximation of fi's to original function. Those are defined as the original values of the function in the beginning. And as we move forward, we again perform the refinable operation on them, meaning we are calculating refinement on the initial points as many times as we require, j times. And this will be the fj's. So practically what is happening that we are performing the refinable operation as we saw in the B-splines for j times. And then we stop. And now we ask ourselves, what is the result of this refinable process? Is it continuous? What can we say about the properties of this process? Is it converging? This is maybe the first thing that we need to ask ourselves. So before going to the results and the proofs of what can we say about them, let us look on the matrices that we just defined. Where are they? Oh, sorry. So those matrices are in some sense, they are block diagonal matrices, not as the matrices as we saw before, the T0 and T1. And actually what we see somehow a symmetry that is happening between those coefficients that we saw that are coming from our refinable equation. And what we also see that the C's are dominating the main diagonal, and the D's are the ones that are dominating the other diagonal. And if I remind you, the C's are coming from the even points that are used in the support, and these are coming from the odd points. We can do the same thing for the M1s. And now the question is, what can we say about our refinable functions given the M0 and 1s? So I skipped it, but let's go over the takeaway message number 2 that I list here. So what are the properties of the new definition? Is it continuous? Yes, we were able to prove it. Is the derivatives of the new refinable function is continuous? Yes. And whether they can be approximated by neural networks again. And the answer is yes. And basically that was the main goal of all this work, to build a neural refinable function that will be easier approximated by those neural networks. So how do we start analyzing this situation? We have the refinable equation of V equals MBI multiplied by V of tau x. Usually what is done is looking on the spectral properties of those matrices and trying to understand whether we can deduce something about the refinement procedure. So in order to start playing with those matrices, we have to think about the spectral radius of those matrices, and also about the joint spectral radius between the multiplication of those matrices. We are not looking of pairwise multiplication, we are looking on the multiplication of MD1 until MDM that are basically extracted from our refinable process. And we will use this raw definition in our proof. So let us just see how it works in a formal way. We have those matrices M0 and M1, and let us look on a joint eigenvalue, left eigenvector of those matrices, and let us look on some space E1 that is n-1 dimensional subspace that is orthogonal to this joint eigenvector. Now, if we are looking on the following definition of the joint spectral radius, we are basically examining the multiplication of M matrices, M0 and M1, restricted to our E1 space. And we are taking the square root. We are restricting ourselves to E1 space that is basically orthogonal to the first eigenvector. And this has something to do with the constraint that we will later require that the C ends and D ends will follow. So basically, what this eigenvector defines as is a space E1, and later we will see that we can construct additional spaces that will follow some rule. Okay, so now let's look on the first theorem that basically states that those functions that we defined before are Holder continuous. So we assume that we have the refinable equation with the masks Cn and Dm, and the sum rule holds. I didn't tell you what are the sum rules yet, but maybe I'll just mention it briefly. What are the sum rules that we are demanding from the dns? So first of all, what we demand from the Cns and Dns, that they will sum up to 1. Exactly like we saw in the original quadratic B-spline. That's the first sum rule that we demand. And this is basically what restricts us to this E1 domain. So now that we have this sum rule that is fulfilling, and we are looking on again on the left eigenvector, we asked that the spectral radius, the joint spectral radius, will be bounded by some C and lambda m. We assume that there exist such numbers that can bound it. In that case, the operation, the refinable operation that we defined before, Fj converges, and not only it converges, but it also converges to the smooth continuous function f that we already initially had. And this is the first result that we worked very hard to prove. The second result that we were able to prove that not only the refinable equation, the new one, converges to something smooth, but also the derivatives are Lipschitz. Now we are talking about additional rules, and I will not list them here because they're quite complicated, but we can require that the Cn's and the Dn's that are the refinable mask will follow additional rules. Besides summing up to 1, they have to follow some other rules that will basically imply that we have now different subspaces that we will define them as EM. And in those subspaces, we just ask that the joint spectral radius with respect to those subspaces of the two matrices will be also bounded. In that case, there exists a non-trivial continuous function f that will be the refinable for the refinable equation. Not only exists, we are able to prove that the solution to that refinable equation is k times continuous differentiable. And not only that, but we can split our discussion based on what is happening to the constant lambda here and add additional information. I'm not bringing you the proofs of those theorems because they're very exhaustive, and if you want to read more, I think that in a week or 2 weeks from now, we'll be able to upload it to the first draft to archive. And the third theorem is that those new refinable functions are, as we expected, can be approximated by the neural networks. So just to give you a sense of what did we do here, we introduced a new refinable equation that can do interesting stuff. Let us play with the well-known quadratic B-spline that we saw before. So this is the original equation, and we can redefine it using our new notations. Basically, for each point that uses the even points, we are using the point from the even point from the mirror across this point. So basically, that's instead of using the point of 2x minus 1, we are using the point of 2 minus 2x. Instead of using the point of 2x plus 1, we are using the point of minus 2x. Now we can define the C0 and the Ci's and the Di's coefficient and rewrite the equation in the matrix form. Now we can see that already the new matrices are different from the one that we saw before, and the block property that we raised before exists here. So what are what is happening? We can rerun all the refinable processes I showed you before with the illustration and still get with the current coefficients of C0 3/4 and C1 of 1/4 the same B-spline. Now we can start playing. I remind you that the C1s and the D1s and C0s and D0s should obey certain rules, and that's basically by defining one of them from each pair of C0 and D, and it will practically define the other coefficient. So let us first vary the coefficients of the C1s. If we had 1/4 before, Now I'm playing again with the same quadratic spline equation, but with different CIs. The first one that I examine is 1/8, and it gives me this function. I can examine what happens in C1 is 1/2, and so on and so forth. I can examine different functions that can be created using only this refinable equation by altering C0 to be 0.875. And I get other functions. I can continue playing the game and generating more and more functions. And I remind you that these is functions that are the ones that are only coming from the quadratic B-splines. Now we can take any other refinable equation that we already know, whether it's the subdivision scheme or the wavelets, and generate new functions in this exact manner. And the question is now, what are the properties of those new functions that are generated? How can they help us, and are they better in some sense in the practical examples where we use those functions? We know that the B-splines are amazing in approximation theory, but are the new non-symmetric functions that we just defined here how and what are the effect on the approximation theory? So the takeaway messages, I know that it has been a long time, but we started with talking about high-dimensional data and manifold reconstruction. We later continued with the properties of approximating refinable functions with the ReLU networks. We concluded with the need to define a new refinable equation that will be also reflector refinable equation. And we were able to show that those functions are not only Holder continuous, but their derivative is almost Lipschitz. So this is the list of papers that my work is based on. And I would like to thank everyone for listening to me. And if you have any questions, I will be happy to answer it now.
All right, let's smash that reaction button and thank the speaker.